puede ser los requisitos de la región. Pensé que, bueno, pues estás hablando de licencia permanente. No, sí, inclusive ahorita que Larsen también ahorita ya tiene derecho a...
So, welcome to this first session of contributed papers in this conference. And the session itself is about logic and semantics. And the first talk will be about metrics and Markov chains, and it will be given by Giorgio Bacci.
Thanks. Can you hear me? Yeah. Okay, this is a joint work with other 3 colleagues of mine, Giovanni Bacci, my brother, Kim Larsen, and Radu Mardare. Okay, let's start with what I'm going to talk about in this talk, so the focus. First of all, recently there has been much interest in quantitative aspects of computing. In particular, there is much interest in quantitative models, like probabilistic models, timed automata, weighted automata, etc., etc. And together with this model, there is also a notion of behavior and semantics for this model. And usual semantic is represented as equivalencies. But when we are talking about quantitative aspects, and there are little differences in those quantitative variables, then a notion of equivalence is a too strong a concept. So it's better to have a notion of semantics that is robust enough. And so the idea is to switch between from equivalencies to distances in order to have a notion of how distance and far apart are two semantics and two behaviors. And together with this, of course, there are also formal verification techniques in order to say something, to check behavioral properties on these systems. For example, quantitative model checking. And in this talk, we are going to see probabilistic models and probabilistic model checking. In particular, we are focusing on linear time properties. Why? What does it mean, first of all? That our observables are only execution runs, so we have no internal access inside the model. And why is this useful? Because in systems biology, if you think about that, you can only inspect the system looking at a certain path of behavior. So you just look at outside as a black box. This is also very useful in machine learning, artificial intelligence, security, where you cannot access the state inside. And now, let's start to explain what are our models. So Markov chains, probabilistic system. Basically, we have a set of states, and then between them, transitions, which are probabilities. So, for example, from the state S0, there is a probability 1/3 to go to state X2. And the sum of all transitions and the sum of all the probabilities should sum up to 1. Of course, we don't want to see and recognize and distinguish apart states that are actually different, but we just want to see what are the properties of those states. So we just decorate the systems with some labels, which are just sets of atomic properties, the properties of interest in our model. And we can see these models as machines that, starting from one state, produces and emits infinite traces with certain probabilities. Okay, when we talk about probabilities, we also need a notion of event, so a measurable set. What are our events? Are paths, infinite paths, okay, so of states that are measurable somehow. And our measurable and sets are formed as cylinders. So basically sets of paths where a certain prefix is contained in a certain set. For example, here the set, the concatenation of elements belonging to the language S0 concatenated with S1, so forth to Sn. And we don't care about the suffix of this. And we call those cylinder sets. And why is it important? Because in this way, it's very easy to define a notion of probability of a path. So starting from a state S, we just define this probability on this cylinder. So emits a path that has a prefix in this set. And from these cylinders, we have a notion of cylinder set construction, actually a notion of sigma algebra. So the smallest sigma algebra contains all those cylinders, whatever is the length of the prefix, and the set of states that that belongs to those sets. Okay, now we talked about linear properties. So what better? Nothing better than linear temporal logic, of course, and so this is the classic one. So we have atomic proposition, the propositional fragment, so a false and implication is enough, and then two operators, temporal operators, the next and the until operator. And the semantics of those formula is just take a formula and then is the set of all paths that satisfy this formula. And here, the satisfaction relation is the usual one. So I'm not gonna bother you with all the definition, but it's the classic one. Okay, this is nice, in particular because if you take the semantics of a formula, this has a notion that is actually a measurable event. We can actually tell and check what is the probability of satisfying this formula. Okay, thanks to this notion, then we have a notion of probabilistic model checking. And probabilistic model checking is a very simple idea. We cannot, in a probabilistic system, just saying that a probability, so we cannot ask our system strong assertions such as this system will never fail. Because we are allowed only to look at the probabilities. We can only say that this system almost surely will not fail, because saying that the probability is 0, it doesn't mean that that event will never occur. Will occur only with probability 0. So the probabilistic model checking problem, it is given an initial state and a model and a given formula, ask what is the probability of satisfying this formula 5. Okay. Now we are talking about probabilistic systems. And so our system that there are some quantities, and of course we also need a kind of notion of approximation. But this kind of semantics is also, and this idea is also very useful when you look at the problem of model checking. We all know that model checking is very useful, is automatic, but it has a great disadvantage that it doesn't generally scale up to very large systems. And so there are a lot of techniques such as model reduction, symbolic techniques, symbolic model checking, partial order reduction, etc., etc. But still the problem of how huge is the system is still an issue. So what you usually do is to reduce the accuracy of the model, so via an abstraction. And as soon as we reduce the accuracy, then we are introducing an error. Now, what is the error we are introducing? We need a notion of distance to say, okay, now I'm switching from a very accurate model to a less accurate one. What are the errors that I'm introducing? And now the idea that our proposed solution is not just our proposed solution, it's to use behavioral metrics in order to quantify this error. Okay, just to explain you this idea again. So we start with the model M0, which is supposed to be very, very big, or impossible to actually do model checking on it. And we have a notion of probability of satisfying a given formula, M0. Now, the idea is to switch to another model, M1, where the model checking problem is, let's say, easier to do, okay? Not as much as impossible as in the first one. And then, of course, we are introducing errors, so the probability will differ from the first model. And now there is an error which is quantified as the difference, the absolute difference of these two values. Now, as soon as we have a distance, we want that this distance should bound the error, okay, of these two models. And this should, of course, hold for all the formulas we are interested to check. Okay, so let's introduce two logical distances. Of course, we want that the distance is a bound, but it should be also the best bound possible. So, among all the possible differences. So, just the supremum among all possible differences in satisfying, probabilistically satisfying that formula. And we define this distance as LTL distance. Okay, very simple idea. The same, we can do it, and it's actually a metric, we can do it also with subfragments. So, for example, just taking, instead of the entire LTL, the subfragment without a next operator. This is very useful, for example, in system biology, where you cannot actually check what will be the next state in line. So we actually need just, so you don't have a next operator, we just ask questions like with the until operator, so it is less powerful. Okay, now, are we done? Okay, those are two distances, are perfect, but now the problem is, there are three questions to ask. First of all, can we actually use these metrics, so can we actually compute these metrics? They are interesting, definitely, but can we actually do them? Okay, and then what can we compute them exactly or not? And if we cannot compute exactly, can we also give approximated techniques in order to compute them to up to any arbitrary precision? And what about their complexity, if we can actually make them? Okay, we answered in this paper these problems via two characterization of these metrics. We have two characterizations. One is a metric that is very known, is called trace distance, and basically it's just the supremum among the all possible absolute differences in the probability of satisfying from a given state S the formula, the event in up to trace equivalence. So we have a set of a measurable set, we just quotient it up to trace equivalence. Okay, fair enough. The same idea is for stutter trace distance, where now the quotient is up to stutter trace equivalence. And it's not surprising that we actually have this characterization theorem for the two distances. One is that the LTL distance actually corresponds exactly in all possible cases, in all possible values, to the trace distance. And the same is for the LTL without next operator, and it corresponds exactly to the stutter trace distance. But okay, this is natural if you know that LTL logical equivalence on LTL corresponds exactly to trace equivalence. That's fair enough. And the same with stutter equivalence and LTL without the next operator. But these actually correspond to look at the values that are actually at 0. What about all the other values? What can we do? And actually, this is a really tricky problem, and it was not really simple to see this characterization. Why? Let's see this tiny but yet tricky example, okay, provided by, and you can find it in Chen and Kiefer Leaks paper 2013. And in this example, they just studied that the distance between the two states S and D is actually, the trace distance is actually this irrational number. Okay, first of all, it's an irrational number. Now it's a problem of how can we compute it? Can we compute actually this distance exactly? So this is the first problem we have. And second, that the maximizing event, so the maximizing measurable set that attains this distance, okay, is actually an omega regular language. So cannot be represented as an LTL formula, of course. So the direct consequences are, first of all, there doesn't exist a maximizing formula that tell that these two systems are a distance, LTL distance, that certain amount of that number. Okay. And second, it is known that the trace distance is decidability problem is still open. So we have given, thanks to our characterization, also the LTI distance is an open problem. And the same happens with the starter trace distance, so the LTI without next operator. And in particular, the threshold problem is whether the distance exceeds a given threshold, it has been proven to be NPR, not even NP complete, NPR. Okay, so the first question, since the decidability is open and the threshold problem is such a difficult problem, can we still give an approximate way to compute these logical/trace distances up to any arbitrary precision? So an approximation algorithm. So now I'm going to present this algorithm just in the case of the trace distance, but this actually is general enough and can be easily adapted for the starter case easily, and in particular is generalized and actually improves so it's mathematically more convenient to use this kind of approach than the approximation algorithm that has been presented, has been given by Chen and Kiefer in this leaks paper, which is of course a very nice algorithm, but it's not really easy to handle if you want to change the setting. With our proposal, it's a bit easier. I'm going to show you why. Okay, what is an approximation schema? We want to compute approximately the trace distance, so the distance between the set S and T. Okay, we don't know this value, but we know that we want to compute it with this arbitrary precision epsilon. Okay, first of all, what do? We take some upper approximant, okay, that are converging to the distance, okay, and each of them are actually computable. But this is not enough because we cannot actually compute distance, the value T of S, the trace distance between S and T, so we cannot actually say that we are close enough, so less than this epsilon threshold. What do? We just take another series that is converging, but now from below to the same value, and also this one should be computable, and now we can just compute the distance between a certain index of this upper and lower approximate. And of course, if this is bounded by epsilon, then of course also the distance, our approximation is bounded within epsilon precision. What do? Okay, let's first talk about the approximation, the lower approximation. We know that this distance can be computed as the supremum among as a trace distance. Okay. Now the idea, since it's supremum, it's very simple. We just take smaller subsets of measurable sets. We just increase them in order to get to the entire sets of measurable sets. Okay, but in order this to be computable, there is a tricky problem, and basically we need sets which are somehow simpler than the entire sigma algebra, and those are the sets that are taking prefixes, okay, up to length 1, 2, 3, 4, 5. So we explore paths with longer and longer prefixes, but this is not enough in order to get the entire set of sigma algebra. So our trick is to check that actually this is a dense subset of the entire sigma algebra in a very topological sense, in a formal sense. So, and this is actually enough in order to compute the supremum, because the supremum of a dense subset corresponds to the supremum over the entire set. There are enough points, and the points are enough close to each other in order to attain exactly the supremum. Okay, this is very useful. What about now? And that is very simple because it was a supremum. But what about now for the upper approximate? Okay, The idea now is to use a dual characterization of the trace distance, which is very similar to the coupling characterization of the total variation distance, if somebody knows it. And basically it says that this distance is actually the minimum, okay, of the value, okay, of computing the probability on the set of let me just go back a bit. Compute the probability on this equivalence, the trace inequivalence. So, and the probability actually is a probability in the product space of couplings. What are the couplings? Basically, couplings can be interpreted as a transportation schedule from one probability to another. So the idea is just to take part of the probability mass from one side and transport it to the other one. Now, the idea is to use this characterization as we have done before and taking subsets of these couplings. Those subsets and the entire union should be actually a dense subset, because otherwise we don't get the infimum at the same way. Okay, how do we define them? We define it with this notion of coupling structure, which is basically just a map that takes pairs of state and maps them to sets, to pairs of words of length k. And this can be seen as a stochastic process that generates pairs of paths, but chopped in multi-steps of length k. Okay, if somebody knows what is a coalgebra, then should be really happy, because you can see actually the idea that is actually a stochastic process, but just in the product space. Okay, now, and the key idea is that all the probabilities are actually couplings of probabilities of doing performing to steps up to k length. And we define this probability starting from this stochastic process and starting from a pair of states, and we take those sets as sets of coupling. Are actually sets of coupling because we proved that for all k's this is actually the case, and secondly, those are increasing in a strange way actually, because they are not increasing like k, another k, but they are increasing in multiples of k. Okay, and we take the union, the entire union, then we have actually a dense subset in the set of all the possible couplings, so the infimum is attained. Okay, to compute the approximate, we actually proved that are actually computable, but we did more because we proved and we gave algorithms to compute each approximate, and each of them are actually polynomial. We proved that, I won't show you this, with other alternative characterization of the lower approximates, and this is actually not a problem, even though are polynomial, because actually the threshold problem is still NPR. We didn't solve the problem, but it only means that we need exponentially the index is increasing exponentially. Okay, now this is the interesting part actually, that we just discovered that the sequence of lower approximate are actually branching metrics. Okay, and actually are just the first upper approximate is the least fixed point of this operator, which uses the Kantorovich lifting of a distance, which is exactly as the definition of the distance, the Kantorovich, so-called Kantorovich distance of the Chernay tool. And this is nice because it has as a kernel, so the set of all pairs that are at distance 0, correspond exactly to the probabilistic Larsen scope probabilistic by similarity. So it's actually a kind of branching metric. And interestingly, this actually, the k upper approximate are actually generalization of this subconcept, where now the kernel is a generalization of a probabilistic bisimilarity, where the bisimulation game is not done at the next step, but after k steps. So we take the probability of given case steps, and then we do the by-simulation game again. Okay, here is the definition. What is actually interesting that if we compare the exact semantics, so the equivalent-based semantics and the metric-based semantics, we have that in both two cases, those approximations are monotone. Both are bounds for the trace and the trace equivalence, but we just discovered that those are actually, in the metric case, the distances are converging to the trace distance, are not converging in the case of equivalencies. And this is actually a counterexample for this. Here we have that the two systems are actually trace equivalent, so S and T are trace equivalent, but for any possible K, those are not. So it actually sees that the one inclusion is correct, the trace equivalence is not included in the union of all possible trace equivalence. This is, okay, let's go to concluding remarks, because, okay, it's done. So we have proposed two metrics for model checking problem, the starter and the trace equivalence, also approximation algorithm via a notion of duality, which is the general idea that is actually very useful and can be generalized in many cases. We also proved that there is this nice notion of convergence of from branching to linear metrics. Those are our upper approximates. As a future work, what about better algorithms? So apply on-the-fly techniques that we actually developed in other papers for the branching metrics, and in a paper proposed in ICTAC2015. And another possible idea is to use other kind of models and to see if this approximation algorithm is actually general enough. And then also explore topological properties of these metrics. Thanks for your attention.
Thank you. So, questions, Moshe?
Isn't it too pessimistic to compute the distance with respect to all LTL formulas other than a particular LTL formula that you are interested in?
Okay, why pessimistic? I would like to be sure. Okay, I agree with you that maybe you are just interested in a subset of properties. So you just want to compare maybe the distance between just a specific formula or a bunch of them, not entire LTL. And actually this can be done, and the characterization and also the coupling, the dual characterization works. The only difference is that instead of using, I can show you a bit here. Here, instead of, can you see the mouse? No. Okay, it's impossible. Okay, instead of using this trace inequivalence, just use the inequivalence with respect to this sub set of logical formats. So this kind of logical inequivalence with respect to this. And the duality principle applies perfectly. So this can be actually generalized.
I think this would be much more practical than computing the worst possible.
Yeah, it's actually very, yeah, I agree with you.
More questions? You mentioned application to system biology, biological systems. What kind of systems do you have in mind?
Actually, with Luca Cardelli, we were looking at signaling systems. And the idea, actually, he just discovered that there is a nice model known that won also the Nobel Prize, okay? The guy that discovered it, which is called the cell circle cycle, okay? Which is a very important model in all cells. And he actually discovered that the optimal model that attains all the properties that this biological system is actually willing to, is a mathematical object that cannot be implemented for real in biology, because this optimal model is not sound biologically speaking. So it doesn't fulfill all the biological strengths that actually. And what is nice is actually that the distance between the optimal one and the actual biological problem is the closest one. And this is actually very interesting. So we can actually apply this metrics also in biology, also to infer what is the best model, maybe.
Okay, thank you again. Oh no, sorry. We have one more question.
Yes. How robust are your techniques with respect to the notion of distance you take between traces? So you take the difference of probability, but
yeah.
For instance, if you are interested in the ratio between probabilities, like for instance in...
The ratio between probabilities. I'm not sure, I have to check, but okay, I cannot really switch to another distance in order to get all this approximation schema, because we are using a duality principle here.
Yeah.
So if we are lucky enough to get this kind of duality principle also for a different distance, so taking the ratio instead of the difference, then our technique is robust enough, but I don't know.
Maybe you can
okay.
towards about this.
Okay, so thank you again. Okay, and the second talk in this session is will be given by Mateus de Oliveira, and it's about modeling second-order logic and the partial order semantics of the place and transition nets.
Okay, thank you for the introduction. And well, I'm a postdoc in the Czech Academy of Sciences, in the Department of Mathematical Logic. And well, as the title says, I will talk about some relationships between immersial logic, monad second-order logic, and the causal behavior of pattern nets. Okay, so the partial order behavior with the causal semantics. So pattern nets are a mathematical formalism that can be used to model several concurrent systems. Okay, so for example, double buffer, mutual exclusion, and producer and consumer. Several concurrent protocols can be modeled by this simple formalism. And I will briefly describe what it is, just in case. So a pattern net consists on a set of transitions that are here represented by squares, and a set of places that are represented by circles. And inside each place, there can be some number of tokens, which are represented by these black dots. And the arrows are labeled with numbers, indicating how many tokens each transition takes from a place and puts into a place. For example, like when there is no label, then you assume that it's 1. Okay, so for example, the B transition takes 1 token from the lower place, puts 2 tokens to the left and 1 to the right. Okay, so if I fire the B transition, then I get this configuration of the net. And I can continue like this, like firing the transitions over and over. But the crucial thing in the pattern net is that you can fire more than 1 transition at the same time. So for example, here now, the transitions A and C are enabled because the A consumes 1 token and there is enough tokens in that place. And the C also 1 token. So when I fire these 2 transitions at the same time, then this will be the new configuration of the net. And I can keep going on, and this will give the behavior of the concurrent system. Okay? And what's the causal semantics of such a pattern net? This is based in the notion of pattern net process that was introduced by the Gilles and Radu in 1983. And it's like intuitively as follows. We start with an event that intuitively loads the places of the net with the initial number of tokens. So for example, this initial event is loading the place 1 with 2 tokens and the place 2 with 2 tokens. And then if I fire 1 transition, for example, I fire transition A, that consumes 2 tokens from each place, then I consume also in the process the two of the tokens that are labeled with P1 and 2 which are labeled with P2, and I create new tokens in these places. Okay, and so on. And then, for example, I can fire the 2 transitions B at the same time, and the B, this shows how a pattern can also be self-concurrent. That the B transition that's labeled P1 in the previous configuration, there were 2 tokens, but the B consumes only 1 token. So you can find 2 Bs at the same time, and it will produce tokens in the same process, the same place as the same. Okay, and so on. I can keep going on, and this gives us a structure that's called a pattern net process, from which we can extract the information about causality in the net. Okay, so we say that one event is causally dependent on other event if there is a path of tokens that leads from one to the other. Okay, and if I now remove these tokens and leave only the events, and I leave only the edges in which there is an edge from one event A to B, if there is a token connecting both events, then this gives rise to a DAG. And if you take the transitive closure of this DAG, then you get a partial order. Okay, so which is a generalization of a linear order, but the only difference is that some of the pairs of events are not ordered. And finally, you can simplify this partial order by representing it by its Hasse diagram, which is the tag with the least number of edges, such that the transitive closure is that partial order. Okay, so the Hasse diagram is just a clean way of representing partial orders. Okay, so I gave here the first main definition of this talk, that is the causal semantics of the pattern net. Okay, so we generate processes and we take the transitive closure of the events. And the second, okay, so the set of all partial orders that are derived in this way, by taking these processes and taking the partial orders, is called the causal behavior of the net. Okay? Or the partial behavior with the causal semantics. So the second definition that I will need to state the main results is the notion of monadic second order logic that Moshe Bacci was talked already. So at least you know something about it. And in the case of the monadic second order for partial orders, you have these variables that represent for vertex variables that are the lowercase letters, the vertex set variables, And you have the atomic formulas that one vertex belongs to a set of vertices. One vertex is smaller than the other, so x is less than y. And the N of x means that the label of the vertex x is A. So from a finite number of labels, okay? And then you can have these Boolean combinations, like the traditional operations of negation, intersection, or negation, conjunction, and disjunction. And the quantification is either on variables or on vertex variables or vertex set variables. So this is what differentiates the monadic second order logic from first order logic, is that exists of the big X and the 4R of big X there, okay? So now we have the two main definitions of this topic. We have the partial order behavior of a Petri-net and the monadic second order logic. And I denote for P of phi the set of all partial orders that satisfy this formula. Okay? So these are the results of the paper. There are five results. And the first one is the model checking of the partial order behavior against monadic second order specifications, which means that given a Petri-net in the monadic second order formula phi, is it true that all partial orders of this net satisfy phi? So this is equivalent to asking whether the partial order behavior of the net is included on the set of partial orders specified by the formula. And this was not known, and previously was known only for pure Petri-nets. That it's a restricted version of Petri-nets in which you cannot have self loops. Okay, but this is a very severe restriction for some applications. Like, for example, you cannot model waiting loop protocols with this kind of pure Petri-nets. So the first result is the lifting of this model checking to general Petri-nets. So now any Petri-net can be model checked against the partial order behavior can be model checked against the monadic second order. So the second result that was not known for, at least I don't know about any work on this, says that the converse is also decidable. So it means that I can take a monadic second order logic specifying a set of behaviors, maybe it's a set of desired behaviors, and I can determine whether it is the set of all these behaviors are included on the behaviors of the net. Okay, so this is not as used as the model checking, but I will the other applications will depend on these results. Okay, so, and I assume here that all the Petri-nets in this talk are bounded Petri-nets, which means that each place holds a constant number of tokens at each execution of the net, okay? So, the third result is the synthesis of bounded Petri-nets from MESL formulas. So, which means that now I give you a formula specifying a set of partial order behaviors, and I'm too lazy to program a Petri-net that has that set of behaviors. Then I can give it to a program that will compute a Petri-net that has precisely that behavior if this net exists. And if it doesn't exist, it will synthesize a Petri-net that has the best approximation for this behavior. Okay, so I will talk about this later. And based on these three previous results, I define a notion of automated correction of Petri-nets, of bounded Petri-nets, and synthesis of bounded Petri-nets from contracts. Okay, so now I gave the content of the talk. So this is the high level, and the main formalism that allow all these results is the notion of slice automaton. A slice automaton is just a generalization of finite automaton, in which instead of being operating on letters, you operate on things that are called slices. So these slices are just boxes. They are digraphs, the direct acyclic graphs, which can be composed with each other so that to form bigger types. Okay. So when traversing an automaton, you can now consider that that each slice is a weird letter on a weird alphabet. Okay, so for example, you could consider automaton over the Japanese alphabet or the Greek alphabet. So now you are considering automaton over the slice alphabet. A finite set of slices. And the thing is that when you read a string of this alphabet, it's just a sequence of slices. And this is called a unit decomposition if each two consecutive slices can be glued together, which means that they can just be matched as if they were a puzzle. Okay? And given such a string of slices, now you can derive a direct acyclic graph by just gluing together all these slices. So it's really like a puzzle. You glue them together and you get a graph. So in this example there, we have that this graph is the result of gluing that slice. And finally, from this graph, from this data, you take the transitive closure and you get the partial order. So which means that since a slice automaton can represent an infinite number of slice strings, then you can glue each of these strings together, and this will give rise to an infinite language of graphs. And if you take the transitive closure of all these possible graphs, then you have the infinite number of partial orders. So basically, a slice automaton is a concise way of representing partial orders, like infinite families of partial orders. Okay. And finally, concerning this automaton, the notion of saturation is that a slice automaton is saturated if for each graph that is in the graph language of the automaton, we have that all possible unit compositions of that graph belong to the slice language of the automaton. So the slice language is the syntactic label, and the graph language is the semantic label. So if I have that for each element from the semantic label, I have that all possible elements are present in the syntactic label, then it's saturated. And the important issue, the important properties of this automaton is that they have several decidability results and computability results. For example, when the automata are saturated, then intersection of the partial order language is equivalent, like it can be inferred by the emptiness of intersection of the slice language, that's syntactic label. And the inclusion of the partial order language, that's also in the semantic label, can be inferred from the inclusion of the slice language, that are just normal regular language in which the decidability is known. And finally, I can define a suitable notion of complementation for saturated slice automaton, that basically the partial order is, the complement of the partial order language is just the set of all partial order that can be covered by a constant number of paths minus the language that's generated by the automaton. And this complement can also be generated by another automaton. So there are several nice results. So what can we do with this saturated slice automaton? So the first result says that, like this was from 2009 and 2010, from PetriNet conference and from Fundamental Informatica, that given any bounded PetriNet, there is you can construct a slice automaton that represents precisely the partial behavior, the partial order behavior of that PetriNet. And furthermore, the graph language of this automaton consists only of the Hasse diagrams of partial orders in the language. Okay, and then subsequently I showed that this automaton is saturated. And using these properties, I showed that given two different nets with equivalent behavior, they have exactly the same automaton. Okay? You can, so this is why it's canonicity. You can really represent the partial order behavior of a PetriNet in a canonical way. Okay, so in such that two different PetriNets with same behavior will give rise to the same automaton. And this was used to solve some long-standing open problems in the partial order semantics of petri nets. For instance, the inclusion of the partial order behavior of petri nets, of bounded petri nets. Okay, that was not known. It was known only for one bounded petri net before, and the emptiness of intersection. And these results follow simply by constructing the saturated slice automaton and verifying whether they are included. Okay, it's not the construction is not simple, but the approach is at least intuitively simple. And the third problem that was solved with this was the synthesis problem that was proposed by Larsen and Gilles, that given a set of partial orders, construct a petri net with that set, with that behavior. And I showed that if these partial orders, this set of partial orders is represented by a slice automaton, a saturated slice automaton, then you can really synthesize such a net if it exists, or you can synthesize the best net if it doesn't exist. Okay? And since the slice automaton are able to represent the partial order behavior of any petri net, then this solves the Lorentz and Gilles problem for the bounded case, for bounded petri nets. Okay, so now what's in this paper? From the technical side. So the first thing is that I parameterized the notion of the partial order language of the net. So I introduced the notion of C partial order, which is a partial order whose Hash diagram can be covered by C paths. For example, this Hash diagram here can be covered by 3 paths. So this is a Hash diagram of a 3 partial order. You can see there is a path in the zigzag. There is two parallel paths. Okay, so the Hash diagram can be as large as you wish, as long as it is kind of thin. Okay, and then I defined the notion of the restricted behavior of a net. That is the C partial order behavior of the net. That is basically the set of all C partial orders generated by the net. So intuitively, if you don't want to, like, it's very expensive to model check the behavior of a whole petri net because the automata are large. So if you know that the behaviors that you want to model check have a kind of they are thin enough, they don't use too much concurrency, then you can try to verify only that behavior. So this is the goal of the parameterization. But this is enough to represent the behavior of any petri net also, because if a petri net is bounded and has any places, then you have that the C times N, this is a B times N. Okay. So when C is equal to B times N, then you have the whole behavior of the net. Okay, it's of the bounded petri net. Okay, so and then a generalization of the result of the expressibility result is that now, given a bounded petri net, I can construct a slice automaton representing only the C partial orders behavior of the net. Okay. So this is the technical aspect of the paper. And another technical aspect is the notion of minimal, like a causally minimal. Okay, so as a bounded petri net is causally minimal for a set if there is no, okay, so, sorry, a BR bounded petri net is a bounded petri net in which you have at most R repetitions of each place. Okay, so if each place has exactly the same number of edges going in and out, and with the same labels, and with the same transitions, then these two places are equivalent. And basically, a BR bounded petri net allows for several equivalent places. And this is important because the causal behavior of the net is affected by the number of repetitions of the places. This is different for other partial order semantics, but the causal behavior needs this. So given a C BR bounded petri net, you can you say that this is minimal for a partial order set if it includes the set, okay, so that set is completely included in the partial order, but there is no other BR bounded Petri-net that also includes the set and is included in the net that's minimum, okay? So basically, it's minimum if it's the best Petri-net that approximates that behavior, that over-approximates that behavior. And again, now I give a parameterized synthesis. So given an automaton, you can synthesize the best BR bounded Petri-net that contains the behavior specified by the automaton. And if yes, you can construct this net. If there is such a net, you can construct. And if there is not, then you can construct the best approximation. This is the goal. And another important technical result is that for any MSO formula, you can construct a slice automaton that generates all C partial orders satisfying that formula. Okay? So now you can, everything is reduced to automata theory now. So you have a set of MSO formula, and you have a set of Petri-net, bounded Petri-net, then you can always construct this automaton, and all the results of the paper will follow from these manipulations. For instance, the model checking. We want to determine whether all the partial orders of the Petri-net satisfy the behavior. So first we construct the automata of the net. Second, we construct the automata of the formula. And third, we check whether the slice language the syntactic language of this automata are included, of the net is included in the syntactic language of the formula. And since the automata are saturated, then you know that the inclusion of the syntactic language implies the inclusion of the partial order language, and vice versa. Okay? So then the over approximation, the same thing. Given the net, you now want to determine the inclusion in the other direction. So it's exactly the same approach. The only difference is that the inclusion you test in the other direction. Okay, so and using these two things, I can synthesize the best net from a Petri-net. Given a formula. Given a formula, you construct the automaton from the formula, generating all the partial orders, C partial orders satisfying this formula. And you use the synthesis algorithm for the automaton to synthesize the best BR bounded net. Okay? So the fourth result is the automated correction of the net. That's like this. I have a net, a Petri-net, and I have a formula specifying a set of correct behaviors. But potentially my net is wrong. Like there are some wrong behaviors on it. So I want to construct another net that preserves all the good behaviors of the old net, but such that has as minimum number of bad behaviors as possible. So this is formalized by this sequence of inclusions that the intersection of these two, the language of the Petri-net and of the formula is included on the second net, and the second net is included on the first net. Okay? And this also can be done by this automata approach, simply by constructing this automata and by doing these manipulations. And finally, the synthesis from contracts is the same thing. Now I have a set of allowed behaviors and a set of bad behaviors. And I want to synthesize a net that has all the allowed behaviors but no bad behavior. And then I can use the automata manipulation to construct this net. Yes, so this is so now I'm concluding because there are only 4 minutes left, and so to conclude this I defined the notion of C partial order, and this gives a parameterization of the representation of the partial order behavior of Petri-nets and of the parameterized synthesis. And then using these C partial orders, I proved that model checking of the partial order behavior is decidable for any Petri-net. and not any bounded Petri-net, and not only pure bounded Petri-net. Then I showed the converse is also decidable. I showed that the synthesis from MSL specifications is decidable. Introduces the notion of automated correction and showed that this is computable, and the synthesis from MSL contracts and also it's computable. So yes, so these are the 5 results, and well, all these results relating this MSL logic and slice automaton and the Petri-nets also indicates that slice automata are very good formalism for representing the partial order behavior of Petri-nets. So yes, that's it. I conclude.
Thank you.
So I'm missing something fundamental about slice automata. Aren't they just regular automata with the alphabet are slices?
Yes.
So why call them a different name? I mean, the alphabet can be anything, as long as it's finite, right?
Yes, but well, the definition is like this: is a finite automaton over an alphabet of slices. So it's a finite. The difference is that. Of course, it's not that the theory of the slice of the finite automata theory doesn't work immediately for a slice automaton. The intersection and the inclusion and etc. doesn't work for any automaton. You have to be saturated. So, and there is no such a notion of saturated finite automaton for over a set of strings. So you have to define it over a set of slices. It doesn't make sense. Like, in fact, if you represent a string as a line, as a graph, that's only a line.
No, but what's special is the letters, when you have a normal alphabet, right?
Yes.
Then you have sigma, then sigma star, everything is a candidate for the automaton.
Yes,
that's not the case for slices, right? The slices don't quite.
But there is one restriction. The restriction is that you can, of course, you can represent the strings of the alphabet, but you have the restriction that each 2 consecutive strings, each 2 consecutive slices must be gluable. So,
but that's a regular condition. So,
yeah,
the whole thing can be done with standard automata.
No. The definition is a standard automaton, but the results are not standard automaton because we need some additional theorems. So this is but the definition is, of course, is defined as a finite automaton over a weird alphabet. Nothing else like this.
My question is just the opposite of motions. You can compose symbols, just a word, but when you compose graphs,
yeah.
How did you formalize it? It seems you need some category theory, push-outs.
Well,
what is the composition of several graphs?
That's very easy to define in graph theory. You just identify the frontiers of the graph, yes. and glue the edges together. So you can define, of course, using any formalism like graph rewriting, but this would be like throwing an atomic bomb to kill an insect, because it's much easier to define directly the notion of gluability of a slice.
So without push-outs?
Absolutely, yes. Like you just it's one line formula. It's defined in the paper, for example.
Okay, so I find
it's just like that. If there are 2 edges in the frontier, then you delete both edges and you add an edge from one vertex to the other. So it's just that. So I don't need to go to push-outs.
Okay. So we have many more questions, but we will only take one.
Okay, thank you. How easy is it to make sure that an automaton is saturated, or how easy is to see if an automaton is saturated?
Well, no, you mean that you give an automaton and this saturated? Yes, this is just stress theory. In fact, if basically you construct the minimum finite automaton, it's just a finite automaton, and if you know that it's saturated and you know that it's minimum, then you have to test, in this case, that each 2 commutations are in Like if you have a transition like this, okay, you have to show that all diamonds are in the automaton, and then this gives the criteria to determine whether it's saturated or not.
Okay, thank you. And can you model check an unbounded Petronet?
No. No, because you cannot. Well, no, because you cannot construct. But at least I don't know how to. Like, no. There is at least not saturated automaton. There are unbounded Petronets which cannot be represented by saturated automaton. But some non-saturated slice automaton can represent the partial order behavior of unbounded Petronet. But then things get undecidable. Intersection is undecidable, and inclusion is undecidable, and everything is undecidable. So that's.
Okay, thank you again. So the final talk in this session will be by Heinrich and we will know the title very soon. It's Undecidability result for multi-line spatial logic.
Thank you for the introduction. So I will first start with a brief motivation of why this logic actually is useful. Then I'll introduce the actual logic. I then show the intuition of the undecidability results. I have two undecidability results. I first show the first one, then the second one. And at the end I conclude with a conclusion and some outlook. So that, in the last few years, there's been a lot of news on self-driving cars. For example, Toyota plans to offer a driverless taxi service by 2020 for the Olympics. Google wants to have their self-driving cars ready for the market by 2020, and they've already accumulated lots of test miles for their self-driving cars. And there's a lot more of these kinds of news. So, and then, of course, there's the question, why do we need formal rules for these? Of course, there's the safety issue, because people are sitting in these cars and then we do not want them to crash. Then bugs in the software may also cause costs, because the cars may have to be called back or something like this. And then also there's the question of liability, because when two cars crash and one is driverless and one was driven by a car, then the programmer does not want to be responsible, and the car company neither. So now, to prove collision freedom for these kinds of driverless cars, usually you would build a hybrid system. And then collision freedom is a safety or a reachability problem on this hybrid system. But of course, reachability problems are very difficult for hybrid systems, and hence colleagues at my university have suggested to separate the reasoning of to separate the spatial reasoning of collision freedom, which is the spatial property, from the actual computation of the dynamics. So from the actual computation of the position of the cars. And then the logic I consider, so multi-lane spatial logic, in short MLSL, is a logic to reason about spatial properties of cars on a motorway. So I introduce the logic. In this logic we have a set of lanes, here numbered by 1, 0, 1 and 2. We have cars which have a position on a lane, and which are located on a lane and have a position along the lane. And as you can see, a car is not just a point, but it is it has also some kind of volume, basically. And our model is quite a big abstraction from the reality. So, for example, a car does not have a steering angle or something. So we assume a car just drives straight ahead. Then with the thick black lines, the current view is indicated. And So this is useful because we do not want to reason about the whole motorway, but only about a final part of it. So because not everything is, because the current situation is not affected by things that are perhaps hundreds of kilometers away. Then the logic. The actual logic is a little bit more powerful than the one I consider here, but I do not need this additional power to prove undecidability, so I show an easier logic. So the atoms of the logic, there we can compare car variables. We can check them for equality. We can state that a part of a lane does not contain any reservations by car, or we can say that some car is located at a part of a lane. Then we have the first order extension with a negation, conjunction, and quantification over cars. And we also have spatial operators. First the horizontal chop operator and the vertical chop operator represented by stacking of formulas. And the semantics of the spatial operators will become clear at two examples I show. Consider this formula here. It expresses that there is a car on the upper lane at the beginning of the view, which has a reservation, and below that car there's some free space. Then right of yes, also your right of that car. There's some free space on both lanes, and right of that, on the lower lane, there are two successive reservations, and at the end we have anything, so at the end we don't care much what is there. And this don't care is expressed by just by true. So let's see why this model I've shown there satisfies the formula at the top. So the first subformula, the leftmost subformula, is evaluated on the subview indicated in red, and we see that the formula re of C it is satisfied because the car C fills the reservation. Then below that we have some free space. Then right of that we have some more free space. Right of that, on the upper lane we have anything which is satisfied by true, and below that we have two successive reservations by D and then by E. And at the end we again have true. So let's have a look at the second example. This example expresses that somewhere in the view we have overlapping reservations. So in the real world, this means somewhere there's a crash. And this somewhere is expressed by surrounding the actual formula, so in this case overlapping reservations, by true statements, surrounding it at the top, at the bottom, at the left, at the right. So let's see how this is evaluated. So the first true is satisfied by this very quite big view in red. Then the true at the back is satisfied by this view, and the formula in the middle is then only evaluated on this small view. And we have now so the top true it is just evaluated on the empty view. So we do not chop off any lanes. It is just empty, and still true is satisfied. Then the big formula in the middle is satisfied by this small overlapping reservations of F and G. And then below that we have some free space which is satisfied by true. So in this modality we abbreviate it as with these angled brackets, and we call it the somewhere modality. And we will use this modality a lot for the reduction for the proof of undecidability. So for the undecidability result, I use context-free grammars. So context-free grammars consists of the set of terminals, here A and B, of a set of non-terminals, and some rewrite rules which we can use to replace non-terminals according to the rewrite rules. So, for example, here I show two derivations. of the same word for two different grammars, the grammar 1 and grammar 2. And we see that the derivations derive the same word. And hence, the intersection problem of these two languages, the intersection of these two languages is not empty. And in general, the intersection problems for context-free grammars is undecidable. Derivations can be represented as derivation trees, as shown at the right. And in my construction, I represent, or a model satisfying some formula represents such a derivation tree. So, yes. Given two context-free grammars, I create a formula f such that the formula f is satisfiable if and only if there's a word in the intersection of the two grammars, as shown there. And to try to give you an intuition, the models satisfying the formula f basically look as shown on the right. So for, the derivation from the one grammar grows from the top towards the middle, hence the subscript d, and the derivation from the other grammar grows from the bottom towards the middle. Yes. For the reduction, I assume that there are no overlapping reservations, so this formula we've almost seen before. It expresses that nowhere, the nowhere comes from the negation, there are overlapping reservations of different cars. Then we represent letters as shown there. So, for example, the letter A could be represented by a single reservation, where the car variable C is a free variable. It serves as an identifier for this special, for this occurrence of the letter A. So we use it to distinguish different occurrences of the same letter. And then B, for example, is represented by two successive reservations. To distinguish, for example, two A's from one B, we require that before and after every letter there's some free space. And, yes. And then words are just successive letters, and the concatenation of the letters is here done by the horizontal job operator. Now I show how the rewrite rules are encoded. I cannot show the whole construction, but I hope to deliver an intuition. So a single non-terminal, for example, non-terminal A, is, for this non-terminal, the rewrite rule is encoded by this formula there. So it says that on the upper lane we have a non-terminal A, which is represented, for example, as I've shown before, by one single reservation. And then below that letter we have a word according to the rewrite rules. For example, here now two non-terminal A's or a terminal A. And in general this is encoded like this. So we branch over all different possibilities for the replacement of the non-terminal N. And now, so the step formula is just the encoding of a single rewrite rule, and now the step all formulas, it encodes that this single rewrite rule is actually applied to all non-terminals in the model. So we say that, the formula says that whenever there is a letter, the representation of a non-terminal n, then to this non-terminal the step rule is applied. Let's see how this, as an example, how this evaluates. So the letter, the non-terminal n, we match it to A, and then the red box indicates a part of the model which satisfies the formula letter free of n. And then the formula says that to this non-terminal the step formula should be applied. And then in red I've shown a subview satisfying the step formula. So because we branch over all variables and over all non-terminals, this is actually applied everywhere in the model. Note that this formula strongly relies on the use of the somewhere formula, of the somewhere modality. Now this is the encoding of one grammar, of the grammar growing downwards, and to encode the other grammar growing upwards, we just flip the vertical chops. So what was before at the upper lane now is on the lower lane. So when there's on the lower lane a letter N, then above that there should be a replacement according to the rewrite rules of the grammar. And the full formula is shown below, at the bottom. So the two-step formulas I have explained. Then also we have an initial formula that says, okay, at the top lane and at the bottom lane we have we have the representation of the starting non-terminal. Then we also have a formula to ensure equality of the derived words that I have not shown, but it uses similar principles, and then we also have some side conditions. For example, there are no orphan letters, for example, only. Now, as the first main result, so by this outlined construction, which is fully given in the paper, I've shown or I've reduced the satisfiability, the intersection problem to the satisfiability problem, and hence the satisfiability problem is undecidable. What I've not shown is, for example, how equality is ensured. And the construction does not rely on density of the horizontal domain, so it could also be a bit discrete in the construction, still works. But however, the construction relies on exact positions, and hence a natural question is what happens if the data is imprecise. This is because the logic models spatial behavior of the real world, and there the data comes from sensors, and these usually work with imprecise values, and hence the question of robust satisfiability is also relevant. So a formula is robustly satisfiable if there is a model M satisfying the formula, and all models similar to this model M should also satisfy the formula. And if that is the case, then the formula is robustly satisfiable. Now the construction I've shown, it does not work for this new satisfiability relation, because we strongly used the fact that the letters are successive non-overlapping sequences of reservations. So when you, for example, consider this model outlined at the bottom right, so when the position of any of the cars is perturbed a little bit, then suddenly this formula shown above that is not satisfied anymore, because either in between the reservations there's some free space which violates the formula, or the reservations overlap, which also violates the first part of the formula. Now we can still show that the robust satisfiability is undecidable, because so for this I used a different kind of representation of letters. This new representation has has some markers on both sides of each letter, and in between these markers we use we just say, okay, for example, the letter A has one car, and the letter B has two cars in between these markers. And hence also the robust satisfiability problem is undecidable. So for our conclusion and outlook and future work, the full logic is undecidable, even if we consider if we assume that the data is only imprecise, and hence some weaker fragments might be useful to consider some weaker fragments. For example, when we only have a bounded number of cars, then the logic becomes decidable, and we have there are some use cases for this, and this we have shown in or this we have considered in some other paper. When the number of lanes is bounded, then the decidability is not clear. So the construction I've shown here, it strongly depends on the number of lanes being unbounded, and I think it still is undecidable even when you bound the number of lanes by some adaptation of the construction I've shown. Yeah, as I said, the logic remains undecidable even when the horizontal domain is discrete instead of dense, and another restriction might be to, or another fragment might be to restrict the comparison of variables, because as you've seen, the reduction also strongly relied on comparison of variables, of arbitrary variables. Also, it might be useful to try to connect this logic I've used here to other logics, because other logics are well studied, more studied, well understood, and also readily used. For example, HS, which is a logic of a propositional logic of intervals, which formalizes or which uses Allen's interval relations. Or perhaps to multi-agent logics, because we are using cars, and then each car, of course, basically is an independent agent, so it makes sense to connect it to multi-agent logics. And that's it. Thank you.
Thank you. So we have a lot of time for questions.
How much time did I use? 20. Oh.
You mentioned the connection to multi-agent logic, but I mean, usually the number of agents is finite in these logics, but that's not the case for your logic, right? I mean, you can have an arbitrary number of cars.
So as I've said, there is how to say, we have studied the case where the number of cars is bounded, and the next step is, or we actually want to consider next the case where the number of cars is bounded, and we consider the cars as independent agents, each having their own, independent logic. Knowledge. So we want to consider an epistemic. I think it's called epistemic logic related to this one.
I'm not sure if I understood correctly the notion of robust formula. Isn't it that you have a topology on your models, and then a robust formula is just that the formula represents the set of the models or sets that are satisfied that formula is just a closed set?
I think I did not get your question at all. Could you repeat, please?
Can you go back to the slide robust formula? Maybe.
Which one?
You say robustness.
I see, robustness, I see. Yes, this one?
It's not sure. My question is that, is a robust formula representing a closed set?
I don't get this last word.
A closed set.
A closed set. So usually, usually a robust, a formula is robust is satisfied. You mean that that is not dashed?
The semantic of the formula. So the set that, yes.
So the semantics of the robust formula is that we can perturb models satisfying the formula, and also the perturbed models satisfy this formula. And this. So perhaps I should have dashed the circle around the model, because usually it's another semantics is that we consider an open ball about that we can build an open ball of positive diameter about a satisfying model, and all models in this open ball satisfy this formula. Does it answer your question? No? Sorry. Perhaps we can take it offline.
Yeah.
More questions? There.
So thank you for the talk. I have a very simple question. How would you go about solving the problem that the cars have different size? Would you choose the size of the car in your logic, that is a C if I'm not mistaken, as being the maximum of the size of a car, or would you sort of like join cars to make a bigger car?
It's not, I mean, in this model the cars do have different sizes. So this...
But somehow you have like lanes, and in a slot you have a car on the upper part and down also. And they have the same sizes, so you can put them whenever you want.
So, I mean, you mean in the reduction, you mean?
Yeah.
So in the reduction, each of these boxes here represents a number of cars. So, for example, the non-terminal SD could be represented by 5 cars, or perhaps the terminal A could be represented by 10 cars or whatever. So in this representation, each box represents several cars, and in this picture, each box, each of these angled boxes represents a single car, and here these single cars may have different
you can group them together afterwards.
Well, yes, that's within the power of the logic. Yes.
Okay. Thank you.
Do you have any idea about bounded number of lanes? Can you perhaps translate it to another logic, like interval logic then?
So, I think yes. So I think it can be, if the number of lanes is bounded, then it can be translated to a fragment of Hypershorn logic. Only to a fragment, because the fragment would, how to say, the domain of the Hypershorn logic would have to be discrete, not discrete, countable. It would have to be countable, because each interval would then correspond to one reservation in this multi-lane logic.
Okay, thank you.
Okay, my understanding of what a logic is a formalism where you can formulate several problems.
Mm-hmm.
So, do we really need to have a spatial logic just for the multi-lane problem, or could you design a more general spatial logic in which you could express this problem?
So, of course, you can always design a more general one, but I think one advantage of doing it this way is that, of course, from the specialization, you have less power, and hence you have easier computationality. But of course, so I think the general idea of trying to, I will not find it, the general idea of trying to separate the spatial reasoning from the actual computation of the dynamics, I think it can be applied to more or less any setting. For example, perhaps also for airplanes, or for for any mobile agents moving through space and time. And this is just one simple instantiation.
Thank you. So if we don't have more questions, we are going to thank the speaker and all the speakers of this session.